duration of the lecture. We encourage you all to ask questions during the lectures, but please do so in the chat. One of the organizers will communicate your questions to the instructor. You will also have an opportunity to ask questions verbally at the end of each lecture. With that being said, we are very excited to have Sahana Balasubramanya speaking on relatively and acylindrically hyperbolic groups. Whenever you're ready, Sahana.
Thanks so much, Macarena. So, as you've already said, my lectures are going to focus on acylindrical hyperbolicity. And I'm sort of going to end up defining relative hyperbolicity using the techniques of, the world of acylindrically hyperbolic groups. So to jump right in, for most of this talk, I'm going to be concentrating on actions on hyperbolic spaces. And perhaps you've seen the definition of a hyperbolic space last week, but just to remind you very quickly what I mean by a hyperbolic space, I tend to think of spaces being hyperbolic via Ripps's condition of thin triangles. So you have a metric space XD, and I always assume that this is geodesic, which means I can connect any 2 points by a geodesic within my space. And my space is going to be hyperbolic if there exists a delta, which is non-negative, such that the following condition holds. So I'm going to pick 3 points in my space. I'll call them X, Y, and Z. And I'm going to connect any 2 pairs by geodesics in my space. So these are geodesics between X and Y, Y and Z, and X and Z respectively. And what do? I construct the delta neighborhoods of any 2 sides of this triangle. So let's say I pick the Y side and I take the delta neighborhood of that. And then I do the same for the YZ side. I construct the delta neighborhood of that. And the condition says if you do this, the union of these 2 delta neighborhoods, that should somehow completely cover the third side. So you can see that in the way I've drawn this side XZ is completely contained in the union of the 2 purple neighborhoods. But the same would be true if you took the delta neighborhoods for the side YZ and XZ. Their union would completely cover XZ and so on for the third set as well. And you may wonder, where does the inspiration for this definition come from? Well, it actually really comes from the geometry of the hyperbolic plane. So this is the disk model of the hyperbolic plane. And you consider 2 points in here, X and Y. In Euclidean geometry, sort of the natural thing to do would be to try and go directly in a straight line between X and Y. That would be your geodesic in Euclidean geometry. However, hyperbolic plane geometry is very different from this. In the hyperbolic plane, the geodesic tends to veer off towards the center of the space and then veer out again. And if you do this for a triple of points, then the same thing is true. And so you end up getting these triangles, which are sort of fat in the middle and thin more towards the ends. And that's where this concept of thin triangles comes from. Okay. Now, of course, I'm going to talk about actions on hyperbolic spaces, but I'm also going to talk about acylindrical actions. And before I give you the definition of an acylindrical action, I just want to convince you that this is a useful notion of an action to study, right? Where does the motivation to study acylindricity come from? So the starting point, of all of this work comes from Bromo's work, who studied proper and co-bounded actions, which perhaps you've heard of as being geometric actions on hyperbolic spaces. And what Bromo did in his groundbreaking work is that he defined hyperbolic groups, which are precisely groups that have geometric actions on hyperbolic spaces. But he also defined the class of relatively hyperbolic groups. And if you don't know what that is right now, that's fine. I will get around to it. But morally speaking, these are groups that are hyperbolic, except for certain subgroups which don't exhibit hyperbolic behavior. So if you kind of ignore these bad subgroups, which are called the peripherals, then the rest of the group has a nice behavior, the kind that you would want from a hyperbolic group. But in geometric group theory, there are lots and lots of groups that have been studied over many, many years that have very natural actions on some hyperbolic space. And examples include, the mapping class groups that act on the curve complex, or right-angled Artin groups that act on the extension graph. And while these actions may be co-bounded, they are definitely not proper. So they're most certainly not geometric. However, it turns out that there were similarities between all these different actions. And, people tried to study WPD actions, WWPD actions, in an attempt to sort of try and find a unified approach to study all these different groups that share a lot of properties with hyperbolic and relatively hyperbolic groups, but didn't actually belong to that class of groups. And it turns out that the unified approach is actually possible by studying an acylindrical action. So acylindricity was first defined by Sela only for groups acting on trees. And then later, the more general definition was given due to Bowditch. So that's the definition that I'm going to give you now. And also, just to remember, I'm always going to talk about actions that are isometric. So for me, if I'm considering the distance between x and y, this will be the same as the distance between gx and gy. So this is what is known as an isometric action. It's distance preserving. And for me, all actions are just naturally isometric. So an isometric action of a group G on some metric space, and this is the notation that I'll use to denote a group action. This is acylindrical if for every epsilon bigger than 0, there exist two constants. One is an R, which depends on epsilon, and the other is a constant n that also only depends on epsilon, such that for every pair of points x and y in X, which are sufficiently far apart, where R is the marker of how far apart these points need to be, the following is true. I am interested in counting the elements of my group that have this following behavior. They don't move X very far, where epsilon is the tolerance of how far away I can move my point. And they also don't move Y very far. And the acylindricity condition says, under these conditions, if you try to count these group elements, then the number of these group elements is at most n. Now, I understand that this may be a very dense definition to understand if you're seeing it for the first time. There's a lot of quantifiers. So let me put up a picture that I hope will sort of help you understand this definition better. What's going on? I'm not interested in what happens to pairs of points that are close by. I'm interested, because of this condition right here, in pairs of points that are quite far away in my space. So I've got X over here, and I've got Y over here. And these are at least distance R apart, which depends on some tolerance epsilon that you've set. And what does that tolerance epsilon do? Well, it defines for me an epsilon neighborhood of my point X. And similarly, it defines an epsilon neighborhood of the point Y. And I'm interested in group actions G that can simultaneously push X within this epsilon neighborhood and also push Y only within this neighborhood. And what the acylindricity condition is telling you is that if you try to count the number of group elements that can do this, there is always at most n elements of the group that do this. So what does that mean? Assuming your group is, of course, infinite. What it means is that if this is the X neighborhood and this is the neighborhood of Y, for all but finitely many group elements, if the X neighborhood moves close, then the Y neighborhood is moving really, really far away. And vice versa, if the Y neighborhood is sort of moving very close for all but finitely many elements, the X neighborhood moves really far away. And there's at most n elements of the group that can sort of do this uniform shift, this closed shift of both the neighborhoods. Okay? So that's acylindricity. And now, in order to explain why it's so convenient, or rather so powerful, to have an acylindrical action on a hyperbolic space, I need to tell you what is a Loxadromic element. So here's another definition. So let G be a group acting on XD, where X is now a hyperbolic space. Okay. Little g belonging to the group is said to be Loxadromic if the map from the infinite cyclic group into your space X. So if this is not clear, this is the infinite cyclic group denoted by Z. The map which is given by map every integer n to the nth power of G acting on X. This is a quasi-isometric embedding for some, and in fact, if it's a quasi-isometric embedding for one little x, it'll be a quasi-isometric embedding for any x, but for some x which belongs to your space. Is everyone here familiar with the definition of a quasi-isometric embedding or a quasi-isometry? Is there anyone who doesn't know what that is? Okay, if everyone is comfortable with the notion, then I'm just going to say it very quickly in words to refresh your memory that a quasi-isometry is essentially a coarse version of isometry. It means that the set of points that are described over here by these powers of G acting on this choice of base point, well, they won't exactly, the consecutive points won't exactly be n apart, but up to a scaling factor and a shift factor, it is roughly n. So these points kind of do define this quasi-geodesic that goes off into your space. And what's the nice thing about having Loxadromic elements when you act on a hyperbolic space? Well, the nice thing is the following, that if X is hyperbolic, then there is associated to this hyperbolic metric space a well-defined object which is called the bromo boundary. And I'm not going to get into the definition of the bromo boundary because it's a bit technical and I unfortunately won't have enough time to get into all the details. However, if G is Loxadromic, then what that gives you is these two pairs of points denoted by G to the plus minus infinity that belong to this bromo boundary. And where do they come from? They come from precisely tracking where positive powers of G shift this base point. That gives you the endpoint, which is denoted by positive infinity. And G similarly, G to the minus infinity comes from tracking where do the negative powers of G shift the space point. Okay, so these points, of course, belong to the bromo boundary, but they also end up belonging to the limit set of G on the boundary because they're coming from this group action. Okay, so now that we know what a Loxadromic element is, I can give you the theorem that demonstrates the power of acylindricity. This is a theorem due to Dennis Osen, and you can think of it as the classification theorem for groups acting acylindrically on hyperbolic spaces. So the statement says, let G act on X, where X is hyperbolic, and the action is acylindrical. Under this situation, I can tell you exactly what your group action will look like. Then exactly one of the following is true. So what's the first possibility that can happen? Well, it could happen that your group actually acts with bounded orbits. There's nothing interesting that is happening, and G acting on some choice of base point just gives you a bounded orbit. So this is what we call an elliptic action. So the action is elliptic. And here I'm actually following the same words that Gromov used when he did a more general classification for groups acting on a hyperbolic space without the condition for acylindricity. But what does this mean? It means G has bounded orbits. So in particular, it cannot have any Loxadromic elements. But moreover, if you try to consider what are the limit points of your group onto this Gromov boundary, there are none. The second possibility is that the action is lineal. And what does this mean? It means that G has at least one Loxadromic element, but all Loxadromic elements share the same endpoints on the boundary of your hyperbolic space. So the lineal action kind of looks like this. Let's say you have your choice of base point x, and little g is your Loxadromic element. So we've got an axis that it defines just by taking its powers. And of course, this doesn't have to be a straight line geodesic. It could be something like this. It could be a quasi-geodesic. However, inside my group G, there exists at least one such element. And if there's any other Loxadromic element, let's say H is another Loxadromic element, well, what does H do? It's also going to translate along this line, so that its limit points that it defines with its respective positive and negative powers are the same ones as given by G to the plus infinity and G to the minus infinity. So what does this mean for the group? It means that the entire action of the group is sort of concentrated in this neighborhood of this quasi-geodesic that's described by the powers of G. And that's why it takes the name lineal, because the group looks like it's acting along a thickened line. But in case of acylindricity, this actually has a very strong consequence for the structure of the group. So because of the acylindricity, this also means that G is going to be virtually cyclic, or rather virtually infinite cyclic. And I will caution you and tell you that if you drop the condition for acylindricity, this implication is no longer true. There are lots of groups. In fact, you can take Z cross Z, and there are lots of ways to make it act on different lines. None of those actions are acylindrical, and of course, the group is not virtually cyclic. But because of the acylindricity, this tells you that in this case, the group is actually virtually C. And the third possibility that can occur, which is sort of going to be the most interesting for us, is that the action is of general type. And what do I mean when I say that? I mean that the group G has infinitely many independent Loxadromics. Okay, we understand what we mean by a Loxadromic element. And of course, infinitely means I've just got an infinite collection of Loxadromics. What does it mean to be independent? Well, this is what it means to be independent. G and H are independent if their axes in the space kind of look like this. So this is the axis for G, along which it's going to act by translation, where positive powers push you towards G plus infinity, negative powers push you towards G minus infinity. And if H is independent from G, then its axis will sort of look like this, where again you have the H plus and minus infinity associated to it, but these two sets are completely disjoint. Okay? So it gives you this sort of nice transverse pair of loxadromics. And what's a very good example to think of a general type action, I think it's one that most of you would be familiar with, it's to take the free group on two generators, and we think of this as being generated by A and B. And I'm going to look at the action on its standard Cayley graph, which is the valence 4 tree. So you've got powers of A that move you in one direction. And you've got powers of B that move you in the other direction. And of course, this is a tree. It's valence 4 everywhere. And this is a non-elementary action. First of all, I think it's easy to convince yourself that, you know, the A, which translates along this main axis over here, of course, you know, the loxadromic A has lots of axes. You could make it act over here. You could make it act over here. But if you look, for example, at this main axis of this element A, and you look at the main axis of this element B, they're going to describe very, very disjoint endpoints on your bromo boundary for this space. But moreover, if you were to take, in fact, any non-trivial word in your free group, and you start looking at what its powers do, and you keep moving deeper inside your tree as you take powers, you'll see that those endpoints are also very distinct from the endpoints described by A and B respectively. So this has infinitely many pairs of independent loxadromic elements. And you may wonder, is there some relationship between, you know, having these infinitely many independent loxadromics and free groups, if, you know, you can sort of see the very common behavior between the two? And the answer is yes. Actually, if you have two independent loxadromics, so if you have two loxadromic elements that behave this way, you can actually show that they generate a free group inside your group. And this is a very popular tool in geometric group theory, which is known as the ping pong lemma. And if some of you are interested in seeing how its proof goes, there is actually an exercise in the exercise sheet that deals with this very lemma and one of its applications to SL2Z. So you can try to see how the proof goes and try to prove it as an exercise. Okay, but what does this tell us, right? This is the end of the theorem. But this is telling me that if my group acts acylindrically on some hyperbolic space, I have extremely strong control of what the action looks like. Either the action's elliptic or the group is virtually cyclic. And these two cases, cases 1 and 2, are called elementary actions. Or at the other end of the spectrum, you have this very wild behavior where you have lots and lots of free subgroups. And this is what is called a non-elementary action. And with this idea in our head, we can actually define the class of acylindrically hyperbolic groups. G is acylindrically hyperbolic if it admits a non-elementary acylindrical action on some hyperbolic space. And because of the theorem that we've just seen, there is another way to think of this. This is equivalent to asking that G is not virtually cyclic and acts acylindrically on a hyperbolic space with unbounded orbits. Because having the group not be virtually cyclic rules out the second case, and the fact that you act with unbounded orbits rules out the first case, and then the only option for the group to act that's left in case of acylindrical actions is the third, which automatically gives you non-elementary behavior. So when it actually comes to checking whether an action is non-elementary, if you know it's acylindrical, it's enough to show that you have an unbounded orbit. Okay.
So acylindrical hyperbolicity automatically implies the existence of a free, non-abelian free subgroup?
Absolutely. And not just one, in fact, plenty of them.
Mm-hmm.
Yes. Okay. I'm just going to say this in words that I briefly mentioned that, analogous to this theorem, which classifies how a group can act acylindrically on a hyperbolic space, there is a more general classification which was due to bromo, where acylindricity was not assumed. And you may wonder, how is that classification different from this classification? Well, Gromo's classification has two additional possibilities. There is the possibility of the action being parabolic or horocyclic or quasi-parabolic. And acylindricity completely eliminates these possibilities. So you go down from having 5 options to 3. So this is a much stronger set of conditions that are being imposed on the group compared to having a general action on a hyperbolic space. Okay, so I've just defined a class of groups. I should convince you that this is a useful class of groups to study. So I'm going to give you lots of examples. And what I'm going to give you is by no means a finite list, but I hope it's enough to convince you that this is a really large class of groups that has lots and lots of interesting examples. So the first example that I'm going to mention are the non-elementary hyperbolic groups. So if your group is hyperbolic, but it's not finite or virtually Z, it's non-elementary, then it is very much acylindrically hyperbolic. And where can you witness this behavior? Well, you can witness this behavior on the Cayley graph of your group. I'm going to use capital gamma as a notation for the Cayley graph of a group. So let me just annotate that. This is the Cayley graph. And you construct the Cayley graph of your group G with respect to some finite generating set. Because it is true that every hyperbolic group, thanks to the Milnor-Schwarz lemma, that every hyperbolic group has a finite generating set, and because hyperbolicity is preserved under quasi-isometry, and this Cayley graph will be Qi to the space that you started with, this Cayley graph with respect to this finite generating set will also be hyperbolic. And it's not so hard to see that, in fact, this action is geometric. It's proper and co-bounded. And it is also not too hard to show. This is another exercise that geometric actions are always acylindrical. However, it's not true that acylindricity is a generalization of properness. There are examples of actions that are proper, but not co-bounded, of course, but are not acylindrical. So it is a generalization of a geometric action, but not only of a proper action. And the second class of examples that I'm going to mention are the non-elementary relatively hyperbolic groups. Rather, I'm going to say the non-elementary finitely generated relatively hyperbolic groups. And if you remember what I said about the class of relatively hyperbolic groups, those are groups that are hyperbolic modulo certain subgroups which miss this hyperbolic behavior. So where do you witness this action? Well, you're going to witness this action on a space which is known as the relative Cayley graph. So how do you construct this relatively Cayley graph? Well, I'm going to take the Cayley graph of my group with respect to this finite generating set that I had. And sitting inside of this Cayley graph, you have the sub-Cayley graphs of the bad subgroups, which are missing that hyperbolic-like behavior. And so what do? I do what is known as a coning off of these subgroups. So I attach a point, one for each of these subgroups and all of their cosets. And what I do is I attach every vertex to this point, and I declare that all of these edges have length 1/2. So that if I wanted to go from one point in my subgroup to the other, I could just go via this point up here. I could go up and come down, and that would give me an edge of length 1 in this graph, as if I'm counting the combinatorial metric. But what does this do? You see, what I've done to my bad subgroups is that I've completely destroyed whatever geometry was inside of it. This is now a bounded space of diameter 1, which is vacuously hyperbolic, and the same is true for all of its copies, which come from the cosets. And you were already hyperbolic outside of these bad subgroups. So you're hyperbolic outside, the subgroups have now been coned off to give you something hyperbolic, and then the conjunction of the two is still hyperbolic. So this becomes a hyperbolic space on which the group does act. It's still co-bounded, and the action is acylindrical. The third big class of groups in here are the mapping class groups. I don't know if you may have heard of these at some point of time during these 2 weeks, but these are groups that are essentially associated to some surface. And where do these act? These act on the associated curve complex. So associated to your surface S, you can build this geometric object called the curve complex, which is basically a complex that's formed because of, if I'm not mistaken, simple closed curves on the surface. And the group, of course, has a very natural action on this curve complex. And who showed that the relevant information in order to include these into the class of groups? Well, let me first say that the non-elementary hyperbolic groups are pretty easy to see that they are in the class. And the fact that the relatively hyperbolic groups are in this class was proved by Osin. But for mapping class groups, you have to combine the work of a couple of people. So it was Mazur-Minsky who showed that the curve complex is hyperbolic. And then the fact that this action is acylindrical is due to Bowditch. And in the higher genus cases, this is also known to be non-elementary, and that puts mapping class groups into the class of acylindrically hyperbolic groups. The next example that I'll mention are right-angled Artin groups. I think you'll hear more about these this week as Rose is talking about Artin groups. And where do these act? Well, these act on many complexes, but in particular, they act on something which is known as the extension graph. And the fact that the extension graph is hyperbolic and the action is acylindrical is due to the work of Kinkoverda. There is another complex associated to RAGs, which is called the Salvetti complex, which I think is something that is more generally considered for cat-0 groups. And so the next class of groups in here is a sort of generalization. We have groups acting properly on proper cat-0 spaces with a rank 1 element. And don't get too nervous because of the words rank 1 element. This is a version of Loxadromics for cat0 spaces. And if your group has such an action, it is acylindrically hyperbolic. And you can derive this by combining the work of Dennis Osen and Alessandro Sisto. You have to use results that both of them have proven. And when you mesh those two together, you can get this result. The next interesting example that I think are the fundamental groups of 3 manifolds. So that's pi 1 of M, where what is M? This is going to be a compact, oriented 3 manifold with either empty or toroidal boundary. And if you don't understand all of these words, it's fine. Here's a simple example to think of in this case. Imagine that you have a solid 3 sphere, like an apple, and there was a worm that lived inside of this apple, and it had bored itself around in a circle. That would have created a torus inside your solid apple, and that's actually a 3 manifold with a toroidal boundary. Okay, and if you consider its fundamental group, where does this act acylindrically and non-elementarily? It acts on the Basser tree that arises from the JSJ decomposition of your manifold. Okay, so every 3 manifold has this decomposition known as the JSJ decomposition, where you can sort of cut apart your manifold into different pieces. Some of those are the boundary tori or the connecting tori, and some of those are atoroidal pieces, and some of them are hyperbolic pieces, and some are ciphered fibered pieces. And when you cut your space up into these components that are much easier to understand, that decomposition gives rise to a Basser tree, and the group, of course, has an action on this tree. And this is, of course, hyperbolic because it is a tree. And who proved the necessary result for this? You have to, again, combine a few results that you know. You have to combine the work of Henry Wilton and Zaleski in order to see that the action is acylindrical. And then you need some work done by Ashok Minassian and Dennis Osen in order to piece together the acylindrical hyperbolicity coming from that information. Okay, and the last class of groups that I'll mention for today is out of Fn. So this is the free group on at least 2 generators, and out is the outer automorphism group of Fn. What's interesting is that we're still looking for a well-identifiable space on which this group acts in the desired manner. So first of all, who proved this? Well, this was proved by Osen. But the way Dennis proved this result is that he used a set of equivalent criterion, which I'm going to be talking about in my next lecture, in order to show that out of Fn is in fact acylindrically hyperbolic. And that's the criterion of having an infinite non-degenerate hyperbolically embedded subgroup, which is something I'll get into in the next lecture. And what you can do with this information of having such a hyperbolically embedded subgroup is that you can construct some Cayley graph of your group, which is hyperbolic, and on which the group does have an acylindrical action. However, out of Fn has a number of very nice complexes associated to it, which are somehow more general or better to study the behavior of this group. And what's not known is if that Cayley graph on which you have this nice acylindrical non-elementary behavior somehow aligns up or is quasi-isometric perhaps to one of these known complexes. We don't know that. And of the existing complexes, I think it's known that one of them doesn't have an acylindrical action. But for the others, the question is completely open as to whether it is acylindrical or not, to the best of my knowledge. So we don't know a well-identifiable complex on which this group has this nice action. There's some abstract space, which is a Cayley graph, but it's not easily identifiable or understandable. And like I said, this is not a finite list at all of the groups that belong in this class. This is an ever-growing list. But I'm going to stop here, and hopefully that convinces you that acylindrically hyperbolic groups are actually turning up in lots of different areas of geometric group theory. We have them arising in the world of surfaces for mapping class groups, for three manifolds, for outer automorphism groups. There's just lots of, for cat0 spaces, there's just lots and lots of interesting aspects in geometric group theory where these groups live. But at the same time, acylindricity is such a powerful tool that there are lots of things you can actually say about this broad class of groups. And so to convince you of that, I'm going to tell you.
One question, Sahana.
Yeah.
For example, example number 5. Did you mention what spaces these groups?
I did not, but I believe you can look at the action on the Salvetti complex.
Okay.
Are there any other questions? Okay. So, large class of groups, but there's a lot that we can actually say with such a general definition. So to convince you of that, I'm going to start listing some properties. And the first one, so let G be an acylindrically hyperbolic group. And I'm going to abbreviate acylindrical hyperbolicity using this notation because it's really long to keep writing acylindrically hyperbolic. And the first property is in fact exactly what Sammy just mentioned, that G has lots and lots of free groups, subgroups. And this is, again, a direct consequence of the ping pong lemma, which you get by sort of harnessing these north-south dynamics that come from these independent Loxadromics. The second property that I'm going to mention is that G has finite amenable radical. This is a result of Dahmani, Girardel, and Osin. And what does this mean? Well, what it means is that G has no infinite amenable normal subgroup. So not only is your group not amenable, because we know that if you contain lots of free subgroups of higher rank, then of course you're not amenable. But if you try to consider normal amenable subgroups of your group, none of them are infinite. The third property, which is also a result of the same authors, is that G is SQ universal. And what does that mean? It means every countable group embeds as a quotient of G. So G has lots and lots of quotients, and it has lots and lots of very different looking quotients, which is a consequence of this property. The fourth property is that you can ask, okay, maybe it's a bit too general to try and study acylindrical actions on hyperbolic spaces. But what would happen if we restricted to a smaller class of hyperbolic spaces, say, for example, something as specialized as a quasi-tree? So that's a connected graph that's quasi-isometric to a tree. So it's not just hyperbolic, it's also sort of asymptotically rank 1 hyperbolic. And it turns out that that makes absolutely no difference to the class of groups. So G admits a non-elementary acylindrical action on a quasi-tree. And this was work that I did as part of my PhD thesis. And in fact, that you can show is that if G is acylindrically hyperbolic, there's not just one such action. You can actually find an infinite collection of incompatible or inequivalent actions that would still satisfy the same property. And similarly, you can find an infinite chain of such actions that would sort of nest into one another as well. So it's a very interesting phenomenon that even the action on a specialized hyperbolic space does not quite identify the group. There's tons of them. Okay, so acylindrical hyperbolicity is stable under the following conditions, right? We're always interested when we have a property for a group, how can we make sure that the property is stable under maybe taking some extensions or subgroups? And acylindrical hyperbolicity in particular is stable under the following phenomenon. So you're stable under extensions with a finite kernel. And you can sort of see morally why having an infinite kernel would be bad. Because remember, with acylindricity, we're concerned with coarse stabilizers of pairs of points that are far away. If your extension had an infinite kernel, then those would exactly stabilize these 2 points, no matter how far apart they are. And that would throw off acylindricity, of course. But it's also stable under taking finite index subgroups. Quotients by finite normal subgroups. And perhaps most importantly, it's stable under taking S-normal subgroups. And you may wonder, what exactly is S-normal? Well, S-normal says for every, so let me write it this way, H is S-normal in G if for every element G of G, the following is true. You consider the conjugate of H by G, and I intersected with my original group H. And normality would have meant that this is exactly equal to H, right? That every conjugate is still the same group. But S normality is weaker and requests that this just be infinite for every G in G. And acylindrical hyperbolicity is stable under this phenomenon, and therefore in particular under taking normal subgroups as well. And who proved these results? This is also a result of Denisov's. And the last property that I'll mention today, although again, this is by no means a finite list of properties, for those of you who are interested in cohomology and homology, G has unbounded second cohomology, which of course means that G is not boundedly generated. So there's a lot of things that one can say about this class of groups, even though it comes with a definition that is just so general. And in particular, this class of groups has a lot of interesting tools and techniques that one could use in order to study the class of groups. And those include, but are again not limited to, hyperbolically embedded subgroups, group theoretic Dane filling, small cancellation, and a bunch of other things. And what I'm going to do in my next lecture is delve into one of these advanced topics. I'm going to delve into the theory of hyperbolically embedded subgroups, and I'm going to end up defining relative hyperbolicity using this notion. And in the last lecture, what I'm going to do is delve into the concept of group theoretic Dane fillings. And if we have some time left over, then I'll talk about my own research work. But for today, I'm going to stop here. Hopefully, this convinces you that acylindrical hyperbolicity is a powerful tool despite being quite general. And if you like, you can start taking a look at some of the exercises that are already there in the exercise sheet if you want to sort of get used to thinking about acylindricity. So I'll stop here for today. Thank you.
Thank you very much.